Hello everyone. So today we're going to go over section 5.2, graphing circles and rectangular hyperbolas. We will begin with a review of standard and general forms. So we are going to be looking at this parabola here. Its vertex is labeled 3, 1, which means its axis of symmetry will be x equals 3. Okay, so next we're looking at what it is congruent to. So if we look at the first few points of this parabola, we have the vertex 3, 1, and the points on either side 4, 3, and also 2, 3. That is to say, if we move one space to the left or one space to the right of the vertex, we move up 2 spaces. So this parabola is congruent to y equals to 2x squared. By combining the vertex with the parabola that it is congruent to, we can now write the equation in standard form or vertex form. And this is how we have y is equal to 2x minus 3 squared plus 1. The equation in general form can be found by expanding the square in the middle here. So we have x squared minus 6x plus 9, and then plus 1 on the outside of the parentheses. Multiply everything by 2, so we have 2x squared minus 12x plus 18, and then the plus 1. Combining like terms gives us the equation y is equal to 2x squared minus 12x plus 19. Okay. So just a quick review and looking at a conic section that we are familiar with. So the other conic sections, ellipses, circles, and hyperbolas also have second degree equations of some form. So the first one we're going to be looking at is the circle with center 0, 0 for today. So the circle to the right, and that is this circle right here, has a radius of 3 and a center of 0, 0. The equation is x squared plus y squared equals 9, or x squared plus y squared equals to 3 squared. And this is a direct result of the Pythagorean theorem. So the idea is, if we draw any triangle on the circle, so something that looks like this. So what we know about this triangle is that, well, first of all, it is a right triangle. It has the point x and y on the circle here. So its x value is x, y value is y. And what we know about it as well is that the hypotenuse must have length 3 because that is the radius of the circle. And so, using the Pythagorean theorem here, we have x squared plus y squared equals 3 squared. And we can draw this triangle elsewhere as well. So for example, we can draw in quadrant 3. Maybe something that looks like this. And once again, we still have the hypotenuse of length 3. And if this is x, this is y, the equation will still hold. Okay, so in general, the equation of a circle with center 0, 0 and radius r is, once again, x squared plus y squared equals r squared. So if we're given the equation x squared plus y squared equals 4, and we're asked to describe what kind of graph it is, we know that it is a circle of radius 2 with center 0, 0. That's it. Part B, the question asks which of the following points are on the graph. So let's start with the point 3, negative 1. So we can substitute that into x squared plus y squared equals to 4. So 3 squared plus negative 1 squared. Well, that's equal to 10. And 10 is not equal to 4. So that's no. The second point, 0 squared plus 2 squared. That is equal to 4. So that point is on the circle. And finally, the last point here, we have negative 1 squared plus the square root of 3 squared. So that would be 1 plus 3, which is 4. So that point is also on the circle centered at 0, 0 with radius 2. So that's no, and then yes, and yes. Okay, so next we are going to be looking at the hyperbola. So starting with the equation x squared minus y squared equals 4, we're going to sketch the graph. But before we do that, we're going to find the x-intercepts first. So to find the x-intercepts, we can simply let y equal 0. So then the equation simplifies to just x squared is equal to 4, which means x is equal to positive or negative 2. That means the point negative 2, 0 and the point 2, 0 are both going to be on our graph. Second consideration is what happens when the absolute value of x is large. So either x is very large number or negative x is really negatively large. So what happens then? Okay, so let's see here. We're given once again the equation x squared minus y squared equals 4. So we know that y squared is equal to x squared minus 4, just by rearranging the terms. So if we square rooted both sides, we have y is equal to positive or negative the square root of x squared minus 4. So, oops, sorry about that. So this is what we're looking at. So the important idea here is when x is large, or when the absolute value of x is large, whether that x value is positive or negative, x squared will be positive and a very large number compared to 4. So, and what ends up happening is that the 4 accounts for very small amount of the difference, x squared minus 4. So this number might as well just be approximately equal to x squared, and then we're simply taking the square root of x squared. So we can say that y is approximately equal to positive or negative x. Okay, and that will give us asymptotes for our hyperbola graph. Okay, so let's draw those in. So the asymptote y equals x, and the asymptote y equals negative x. Okay, so from there, we can use a table of values to find the rest of the points to draw this curve. And it will look something like this. Let's see here. Just want to make sure to graph this correctly. So if x is equal to 3, point will be approximately here. And here. It is symmetric, so when x is equal to positive 3, so the location again, just using a table of values, so let x equals negative 3 and then solve for y. So for example here, let's say we let x equals negative 3, and then we solve for y. This is what's going to happen. So then, of course, we can rearrange the term. 9 minus 4 is equal to y squared. So y is equal to positive or negative the square root of 5, which is what we have in these two locations. And of course, the idea here is if this were positive 3 instead, it will still give us 9 minus 4 and the square root of 5. So these 2 points will be on the right side. Very similar work can be done with negative 4 and positive 4, which will give us points approximately here on our grid. So that will be 16 minus 4, so square root of 12 is what we have. So yeah, so let's just label one of the points as an example. This is the point negative 3 root 5. And this is the point negative 4 square root of 12. Okay. Yeah. And the rest of the points can be found in a similar manner. Okay, so now what we can do, of course, is draw a curve through the points. So something that looks like this. Of course, the curve will approach the asymptote as x approaches negative infinity on the left-hand side. Likewise, when x is approaching infinity on the right-hand side. So the blue part is the actual hyperbola here. Okay. The two lines y equals x and y equals negative x, those are asymptotes. But the actual graph is just the blue curve. Okay, so notice here the point negative 2, 0 and the point 2, 0 are where the curve changes direction. So those are called vertices. So each one is a vertex. So there's a vertex to the right and a vertex to the left. The point in the middle between the two vertex, which is not part of the graph, this point right here at 0, 0, this is called the center of the hyperbola. And the other piece of information that's important here is that the line segment connecting the two vertices is called a transverse axis. So this is this line right, this line segment right here. This is the transverse axis. So a bit of new terminology, but the important thing is that a hyperbola has two parts. So the blue curve on the left and the right is bound by these asymptotes we can find if we allowed x to be very large in this case. And each part of each curve will have its own vertex. The point in the middle is the center of the hyperbola, and the line segment connecting the two vertices is the transverse axis. Okay, so the question might be, instead of what happens if we have y squared minus x squared equals 4 instead of x squared minus y squared equals 4? Then we still have a hyperbola, but the orientation will be different. So here, on the left, we have x squared minus y squared equals 1, which gives us a rectangular hyperbola because it's so-called a rectangular hyperbola because the asymptotes are perpendicular to each other. We can have hyperbolas where the asymptotes are not perpendicular, and that's totally possible. But for now, we're just focusing on the rectangular hyperbola. So in this case, we have x squared minus y squared equals 1. The vertices are on the x-axis. On the right-hand side, this is what happens when we have y squared minus x squared. Instead, in this case, it is equal to 1 on the right-hand side. And as we can see, the vertices are on the y-axis. So the variable that's leading, that's where the vertices will be on that axis. Okay. So in this case, then the vertices for the hyperbola are plus or minus 1, 0. And then here, the vertices are 0, plus or minus 1. The vertices are y equals positive or negative x. And on the right-hand side, same thing, y equals plus minus x. And later on in this unit, we are going to start translating and changing the shape of these hyperbolas and also of the circle, which makes the ellipsis. But for today, we're just looking at the circle with its equation x squared plus y squared equals r squared. And then we also looked at both the rectangular hyperbola with the vertices on the x-axis, that is x squared minus y squared equals a squared. And then if it were to have the vertices on the y-axis, it becomes y squared minus x squared equals a squared. And that's it. So that's it for today. Once again, thank you for listening.